Okay, so let me start by writing down propositions 1 and 2, which we discussed last time. Okay, first I need to say recall what is elementary and boarding. So suppose we have a knot K in S3, possibly wild knot, and we have Q and Q prime in its complement. This will be piecewise linear knots. Actually, it doesn't matter if they are piecewise linear or not. And then I say that Q and Q prime are elementarily unbordered if they're the conjugacy classes that they determine in the fundamental group of the complement to K are equal modulo the nth commutator subgroup. So here n can be integer or half integer. And I hope I don't need to give more details here because it was discussed previous 2 times. Okay, proposition 1. So, in the above notation, Q and Q prime are always two-bordered. And proposition 2 there exists a wild knot K and its meridians Q and Q prime such that Q and Q prime are not elementarily 2.5 bordered. Is everyone okay with these statements and definitions? Okay, so in the previous seminars I gave 2 proofs of proposition 1, an algebraic proof and a geometric proof. Although in the geometric proof there was a lemma, a construction of a Seifert surface. Sorry, I didn't say. I think I should say here that the linking number of Q. Maybe I can say this in proposition 1 and 2, but okay. If the linking number of Q with K and the linking number of Q prime with K equals 1. Okay, so yes, so there was a lemma about constructing a Seifert surface for a node in the complement of K, which has zero linking number with K. So the lemma says that it has a Seifert surface in the complement of K, and this lemma, the proof of this lemma was, I think, not entirely satisfactory. There was a sketch, but so and then today about 1 hour and a half ago, I received an email from Andreas where he raised many questions about both proofs of proposition 1. And apart from this lemma, which I agree was not presented well, I think all his questions are about algebraic topology, which I am using. So he is asking what is cohomology with compact support, which is used in the accurate proof of that lemma. What is the Penchakin construction? What is Tinrod homology? What is Čech cohomology, or how to use Čech cohomology? So these are good questions, and maybe it's a pity that they were not asked during my previous talks. But to answer all these questions, it would take quite a lot of time. And yeah, I think so. Some people may know this stuff, like Piotr Mikhailovich could know this, for example. And other people could know something at least. So I suggest that we postpone proposition. We can try to return to proposition 1 later. But strictly speaking, to discuss all this algebraic topology, it would take at least one additional seminar. So maybe we can try to start discussing at least this lemma about the effort surface today, and then we'll see. But now let me just finally start proving proposition 2. And then after the break, I do want to give some motivation for the definition of n-bordism. Why I'm using this definition. And then after that we can return to proposition 1. Okay, so now we start proving proposition 2. Yeah, okay, maybe before I do that, let me also recall a lemma. So there were two proofs of proposition 1 which I discussed, or at least tried to discuss. And there was a third proof which I didn't try to discuss and don't want to try to discuss it now. But it proves the following lemma, which I just want to state. So if Q and Q prime are elements of a group G, where G is a meta-abelian group, which means that G prime prime equals 1. And also the abelianization of G is isomorphic to Z, and Q prime map to the same element of Z, same generator of Z. Then Q and Q prime are conjugate. So this is this implies proposition 1, and this is proved by just using commutator identities. No Steinrod homology, no Chekhov homology, no infinite Seifert surfaces, also no Alexander module, just group theory and commutator identities. But I think it's a little bit boring to discuss these commutator identities, so I'm not going to do this. But the reason why I recall this lemma is because I want to do the following example. There exists a group G such that G 2.5 equals 1. So it is not metabelian, but it is 2.5 solvable. It is solvable of length 2.5. The next which goes after metabelian. Then there also exist Q and Q prime in G, and the abelianization the abelianization of G is again isomorphic to Z, and Q prime go to 1 in this Z under the abelianization map. Yeah, so here they belong to G, and there is a map from G to Z. But Q and Q prime are not conjugate. So, before proving proposition 2, before doing a geometric construction, let us do an algebraic construction. So it's essentially we want to prove proposition 2 on the algebraic level. And it will turn out that we can directly use this example to prove proposition 2. Any questions so far? Okay, so before I construct this G, let me suppose that such a G is already constructed and deduce some consequences. So suppose that such a G has been constructed. Obviously, we want to construct such a G because if we want to prove proposition 2, so if we proved proposition 2, then such example is obtained in particular because we can take the fundamental group of the complement to K as G, the quotient by the this derived term. So take, assuming that proposition 2 is proved, take G to be the fundamental group of the complement to K modulo this 2.5 derived term. And then this will be obviously satisfied. The abelianization is Z because this is the complement to a knot. and they are not conjugate because it is assumed here that Q and Q prime are not elementarily 2.5 bonded. Okay, so this example is motivated by proposition 2, and now I want to motivate the construction of this example. So to motivate the construction, suppose that such a G has been constructed.
Okay,
Yes?
I ask a question.
Uh-huh.
In your lemma, when you say, can you hear me?
Yes?
Yeah, in the lemma, when you say G and G prime go to 1, that's not 0.
Q and Q prime. Q and Q prime go to 1. That's 1 the generator of Z.
Okay.
So if you look at the complement to a knot, the abelianization of its fundamental group is the first homology of the complement, which is Z by the Alexander duality. And then if we have meridians, if Q and Q prime are meridians, then they have linking number 1 with K, or maybe -1, but we can fix orientation so that it is 1. And if the linking number is 1, then this go to 1 because the linking number is a class in one-dimensional homology. Okay?
Is that lemma true if G and G prime go to the same value? Does it have to be 1?
I think it is true, yes. Yes.
Okay.
Now I am doing example which says that the lemma is not true if we replace double prime here with 2.5. So suppose such a G has been constructed. So we have that the abelianization of G is Z. Then we have a short exact sequence. 1 goes to G prime goes to G goes to Z. So this is exact. And also it splits. Because Z is free, so you can always map a generator of Z somewhere, so it comes back to the same generator, and then it extends to all of Z. So then G is isomorphic to a semi-direct product of G prime and Z along some automorphism phi. So phi is an automorphism. Okay. An automorphism of G prime. So what is phi here? So if this is F, then phi of G equals G conjugated by F of 1. So it's a standard action of Z on G prime by conjugation. And this is, do I need to explain what is a semi-direct product? Yes?
Это так получается всегда, когда есть расщепление, да?
Uh-huh. Okay, maybe not yet. So also then so to say that G is G is 2.5 solvable. So what is G 2.5? It is the commutator subgroup of G prime and G prime prime. So maybe I should recall that G prime is the commutator subgroup of G and G, and G double prime is commutator subgroup of G prime and G prime, and G 3 prime is the commutator subgroup of G double prime, G double prime. And this G 2.5 is between these two. And namely it is the commutator subgroup of G prime and G double prime. Okay, now this let me call this G prime H. Let me use a new letter for G prime. And this is the same as the commutator subgroup of H and H prime. So to say that this equals 1 means that, or you can also write it like this: H and then the commutator subgroup of H and H. So this is equivalent to say that H is nilpotent of class 2. No, of yes, of class 2, yes. Nilpotent of class 2 means precisely that this bracket equals 1. So, okay, if we manage to construct such a group G as we want in this example, then G, so the result of this discussion is that G is isomorphic to a semi-direct product of H with Z, where H is nilpotent of class 2. And so we want to, so this is a necessary condition in order for us to construct such a group G. So we might want to seek G in this form. So seek G in the form of a semi-direct product H with Z, where H is nilpotent of class 2. But we actually want H to be the commutator subgroup of G. And if we just seek G in this form, H is not necessarily a commutator subgroup. So let me say it. If additionally H is the commutator subgroup of G, then we have G 2.5 equals G prime prime equals H prime equals 1, because H is nilpotent of class 2. And here we are using that H prime equals G, H equals G prime. And then G will be solvable of length 2.5, which is what we want. So first of all, I want to prove the following lemma, that H equals G prime if so here we had this automorphism phi of G prime, which is also an automorphism of H. So phi is also an automorphism of H because H is G prime here. But okay, maybe I should forget this all and write here, because here we don't know that H equals G prime. So here we know that G is isomorphic to this semi-direct product, or I should say equal actually here, and here there is some phi. Yes, so the semi-direct product should be along some automorphism. So phi will be an automorphism of H. And also we have, let's call it phi bar. It's an automorphism of the abelianization of H, which is induced by phi. So the lemma says that H equals G prime if phi bar minus the identity is an isomorphism, if I'm not mistaken. Is surjective. This is enough.
Минус, потому что абелиан просто.
Yes, this is an abelian group, and so we can subtract. Automorphisms. We can subtract homomorphisms. So this is a homomorphism. But if the lemma says that if it happens to be surjective, then actually H equals G prime. Is everyone okay with this statement? Okay, so now let me then prove this lemma. Proof. So let me prove it geometrically. So G. So let me consider BH, which is KH1 the Eilenberg-MacLane space with this fundamental group and no other homotopic groups. So then I claim that G is isomorphic to the fundamental group of the mapping torus of an automorph. So phi induces an automorphism. Maybe I should call it phi capital from BH to BH. Okay, let me draw a picture. So there is some space BH with a base point, and then there is some map. So phi is a continuous map, which induces phi small on the fundamental group. So there exists such a map phi capital such that its induced homomorphism on the fundamental group is phi small. And the construction of such a phi capital is standard. You can construct it on the one-dimensional skeleton by considering the images of the generators under phi small. Then you extend it to the two-dimensional skeleton by using the fact that phi is an automorphism of H, so the relations hold both in the domain and in the range, and then you extend it to the 3 skeleton and so on by using the sphericity. Okay, so we have such a map F capital from BH to itself, and we can consider its mapping torus and I claim that the fundamental group of the mapping torus is G. Well, how to...
Что такое вот это?
Тор отображение, mapping torus. So how to define MT? So MT is the quotient of BH times I times 0, 1 by the equivalence relation, which is defined as follows: x comma 0 is equivalent to f of x comma 1.
F кто?
Sorry, phi.
Phi.
Yes.
То есть
So,
вот буквы М и Т, они... Да, понял, да, спасибо.
so I should write MT of phi, but maybe it will let me omit this phi, because this is the only mapping torus that we will use. So yeah, I think I should draw it like this, because the base point should go to itself. It's a base point preserving map, of course. So, well, if you start at the base point and just go along the generator of this mapping torus and then go back to the base point, you get, well, you get some element. You get some element. So I claim that it can be identified with the generator of this Z. So I claim that H can be identified with the fundamental group of this subspace, and Z can be its generator can be represented by this loop. So one thing to verify is that if you conjugate by this loop, if you conjugate some element here, by this loop, then you get what you would get in G under such conjugation, and in G you would get the image of So if this generator is called T, or maybe it can be called 1 in Z, but I want to use it as an element of G, so maybe it's better to call it T. So then the conjugation by T in this semi-direct product is the same thing as for an element of H. If I take an element from H, then its conjugation by T is the same thing as taking phi of H. This is more or less from the definition of this semi-direct product. So I want to check that conjugation by this loop. So this is my element H, a loop representing this H in BH. And if I conjugate it by this T, then I must get phi of H. Well, indeed, what is this conjugation? This conjugation is so H conjugated by T is T inverse HT. So T inverse, T goes here. T inverse, then H, and then T. Well, I can simply now push this loop along the mapping torus, and then this T just gets shrunk, and this loop is just carried on somehow until it gets here. But we do this gluing along phi capital, and phi capital is phi small on the fundamental group. So when we do this pushing, T is gradually erased, and what we get in the end is this loop, which is phi of H up to homotopy. So I think in order to prove this isomorphism, one probably needs to say some additional words. I think what we did here is we constructed a map from this fundamental group into G. So H goes to the fundamental group of BH, and the generator of Z goes to T, and then we checked that indeed the relation here which we get from the semi-direct product is satisfied. So we constructed a homomorphism, and it's more or less clear that it is surjective, because if you have any loop in this mapping torus, you can squeeze some parts of it into BH, and then what remains can be squeezed onto T. And maybe it is not so clear that it is injective, but probably one should apply Seifert-von-Kampen's theorem to prove this. So let me leave this. As an exercise. I think you can also argue geometrically to prove that this map is injective. You can consider some loop which goes to 0. Well, I don't know. I think this is well known. If you open any book about H-N extensions, then you can find this lemma there. So this is also a special case of an H&N extension. And if you open some book in combinatorial group theory like Magnus Carus Solitaire or Linden Schub, I think you will find this lemma there. So it is well known. Okay, so now we want to prove our lemma that H equals G prime if phi bar minus the identity is surjective. So in order to prove this lemma, let us consider the long exact sequence of the pair B MT comma BH. In homology. So we have H1 of, where should I start? H2 of MT BH goes to H1 of BH goes to H1 of MT goes to H1 of MTBH and goes to H0 of BH. Now what is H I of MT BH? Well, it is the same as HI of BH cross I, BH cross the boundary of I is the unit interval. So this is more or less by excision. Or more precisely, you can map this pair into this pair So it's a map excision. Action.
Как переводится excision?
Вырезание. Вырезание. Знаете, вырезание?
Если это аксиом, то...
Okay, so here in the picture, you can take a neighborhood of this BH. So, well, it's not really necessary to go to the bottom, but it's better to, yes. So let's take its upper part of this neighborhood. So. So this is essentially a copy of the mapping cylinder of phi. Okay, and this mapping cylinder of phi, the formation retracts onto BH. Now, yes, so I can certainly write that this is isomorphic to HI of MT, comma, this mapping cylinder of phi. So this is from the homotopy axiom, because actually this pair is homotopy equivalent to this pair. You can write down such a homotopy which makes this deformation retraction and then extends it to the entire mapping torus. Now this is the same as this by usual excision, because here at the bottom you have a copy of BH, here at the top you have a copy of BH, and between of them you have a copy of BH cross I. So this is usual excision, and yes, so then what is this? So this is isomorphic to HI minus 1 of BH. And this is because this is a suspension isomorphism, if you wish. This is essentially a suspension and over BH, or geometrically, if you have some cycle in the bottom, you can multiply it by I, and you get a relative cycle in BH cross I, modulo BH cross top and bottom. So it's more or less clear that so this gives you a map from here to here, and it's easy to see that it is an isomorphism.
Селективность не была совсем понятна.
Well, you can deform if you have any complicated cycle. you can always you can make it straight near the top, and then whatever remains you deform to the bottom by homology, and then you get some cycle in the bottom.
Простите, что вы сказали on the top?
So if you have some complicated cycle in this cycle of this pair, then you can assume by using homology that it is a product near the top. And then you deform everything else to the bottom. And then it disappears because it's relative homology. And you just have such a straight cycle. But it can be proved algebraically in many ways to do it. So I can write that this is H1 of BH, and this is H0 of BH. Now, what is this map and this map? So let us look at this isomorphism more clearly. So we identify the top and bottom of our cylinder with this BH and this BH, but the way they are glued is along phi capital. So and this is the boundary homomorphism. So if you apply it to this group, it will give you, so if you apply it to this cycle, it will give you its boundary, which has two parts. One part in the top and one part in the bottom. So these two parts in the top and in the bottom correspond to loops in the bottom copy of BH and in this top copy of BH, top in the sense of this cylinder. But they are identified along this phi. So I claim that here you get phi bar minus the identity. Is this claim okay with everyone? And similarly, here we obtain the induced homomorphism in zero homology. So this phi, it induces homomorphisms in all dimensions. But in dimension 1, so this is in dimension 1, and in dimension 0, it is the identity, because BH is connected and this phi is not doing anything to this generator. So here we get identity minus identity, which is 0. And this phi bar minus the identity is precisely what we wanted here. Okay, so can I erase this? Now, if this homomorphism is surjective, then this has to go to 0. This will be the 0 map. This is also the 0 map. And this group is Z. Because BH is connected. So we get that this is Z as well. And this is H1 of MT is the abelianization of G. because E pi 1 of mt is G. And this is the abelianization of H. So we get that we get two things from this. First, the abelianization of G is Z, which we didn't know because we constructed G in this form and it was not obvious what is its abelianization. And the second thing which we get is that the homomorphism from the abelianization of H to the abelianization of G is 0. So it follows from this that H lies in G prime. Well, 0 is in the additive notation. If you want multiplicative notation, it would be 1. And also we get from this that G modulo G prime is a quotient of G modulo H, because H lies in G prime. But this is isomorphic to Z. Here we have it. And G modulo H is also isomorphic to Z, because G is the semi-direct product of H with Z. So we have a map from Z to Z which is surjective. But such a map has to be an isomorphism if it is surjective. It is just a property of this group set. It's called Hopf property.
А у нас изначально нельзя было сразу установить, что же штрих лежит ваш.
Но вот этот аж
без
лежит.
такой вложенности. То есть сейчас вот мы вроде бы из того, что аж лежит же штрих, говорили, что же штрих лежит ваш. А сразу этого не было.
I don't think the reverse inclusion can be proved without these arguments, because we have used that phi minus the identity is surjective. If this is not true, then what happens? And if this is not surjective, then this is not 0. And we have some additional summand here, maybe. Something additional here.
А вот это рассуждение в обе стороны работает, получается.
You mean this is invertible?
В смысле, если бы же штрих было, если мы знали, что же штрих лежит ваш, то также вывели бы, что аж лежит же штрих.
I don't know why.
Нет? Ладно, простите.
Well, maybe this can be simplified. I don't know, but it looks like you have to use this assumption. So it looks like the lemma would be not true without
Да,
this
просто она
assumption.
нужно использовать для того, чтобы доказать, что h лежит в штрих. А то, что штрих лежит в могло быть так быть.
Okay, I don't know, but even if I prove that, the reverse inclusion in some other way, how would it help us?
Никак, просто стало ясно, что это было изначально. Без субъективности.
G prime less than H. Well, yeah, probably for a semi-direct product, its commutator subgroup. Well, it can be proved, yes, but I don't see how it would help. Maybe it can be used somehow. Well, anyhow, we wanted to prove that H equals G prime. And well, here we have a map from from G modulo H to G modulo G prime, which is a quotient map. It is not just some random map. So, and this map turns out to be an isomorphism. So we get that G prime is the same as H. So the lemma is proved. Any questions?
А вот изначальная лемма чисто алгебраическая, а доказательство использует вот это топологическое пространство. Неужели нельзя вот без топологических пространств, без гомологий, вот как-то алгебраически быстро?
Okay, Misha asks if this lemma can be proved algebraically. The answer is yes. It can be proved algebraically by using group homology of groups, for which there is a very similar short exact sequence. And actually, it can be proved that it is the same short exact sequence. But if you look at the paper where this long exact sequence for group homology is proved, it's something quite complicated. So it's just a lot of algebraic arguments which for topologists look strange. So I think for a topologist this argument would be more understandable than the algebraic proof. Sorry. Alright, so we have this lemma. Now I can erase its proof, I think. And I think to use some long exact sequence to prove this lemma is quite natural, because the lemma itself says something about the abelianization, and the abelianization is the first homology of the group. So it's natural to consider homology. Well, the question here, the connection between algebra and topology is not so trivial here, because this mapping torus need not be spherical. So this is some difference between the algebraic and the topological approach. or you have to prove that it is a spherical. All right. So we want to to construct such an example, an algebraic example of a group with trivial derived subgroup of length 2.5, whose organization is Z, and such that there exist non-conjugate elements which map to the same generator of Z. And we seek G in the form of a semi-direct product of H with Z, where H is nilpotent of class 2, and phi satisfies this condition. Phi bar minus that entity is surjective. All right, so let's take for H, let's take the free nilpotent group of class 2 on two generators. So this has the following presentation. It has two generators and two relations. The commutator, which basically say that the commutator commutes with everything. The commutator of x and y commutes with x, and it also commutes with y.
Тут все равно на какой из мест коммутатор ставит?
Все равно. Because this relation says that this commutator commutes with x. If you exchange them, it will say the same. G inverse H inverse GH equals 1 is equivalent to H inverse G inverse HG equals 1. Because you can conjugate both sides by H here. If you conjugate 1 by H, nothing happens. If you conjugate this by H, well,
Все правильно.
H.
Слева.
No, it's not quite like this. Well, this can be proved somehow. Yes, and also it is the same as the discrete Heisenberg group. So this is the group of the following matrices. I think 1, 1, 1, A, B, C, and 0 here. And wherever A, B, and C are integer. So when you multiply these matrices, you will find out that it has the same multiplication law as this group. And what is the multiplication law in this group? So x, well, first of all, I have to say that every element of this group has the following form: x to some power n, y to some power m, and then the commutator xy to some power k. Why is that? Well,
Простите, вы произнесли фразу multiplicative law.
multiplication law, закон умножения. So why every element is of this form? Well, every element is certainly a word in x and y. So it is of the form x to ny, y to n2, x to maybe m1, x to n2, y to m2, and so on up until some point, y to nr, x to nr, y to n1. And then you want to bring all x's to the left. And it is possible to bring all x's to the left because you can exchange x and y. So if you have yx, it is the same as xy together with the commutator yx. So this commutator is y inverse x inverse yx. And as you see, these two cancel out, and what remains is yx. So you can exchange x and y like this at the cost of adding a commutator, this commutator, and then this commutator will commute with everything else. So if you have some letters after this commutator, you can move them in front of the commutator without changing anything, because you have these two relations. So in this way, you can bring all x's one by one to the left, and you will just have more and more of such commutators. So in the end, you will have this form. This is called a commutator collecting process. Or collection process. And actually this is the simplest form of the commutator collection process because we have these two very strong relations. And if we have weaker relations, for example, if we have an important group of class 3 or 4 or more, then similar things can be done, but then there will be more complicated commutators here which appear in the same way in the collection process, because when you want to exchange this commutator with some letter, it may be not possible to do it directly, but it can be possible to do it at the cost of adding some more complicated commutator. And these are, so there is a finite collection of basic commutators, which, so there is some normal form theorem for example, three nilpotent groups, which start like this, and then there are some other basic commutators. Okay, so what is the multiplication law? If we have this element xm, yn, xy to the k, and we multiply it by another one, x to the power m prime, y to the power n prime, and the commutator. Sorry, I think here I want yx because here I had yx, and it is not really important, but this is how it works in this basic. So this one is the basic commutator, and xy is not the basic commutator. So I prefer to use yx. K to the power k prime. So how do I multiply them? Well, I want to bring this axis to the left, and so I have to exchange x and y with each other, n times m prime times. And so what I get is x to the power m plus m prime, y to the power n plus m prime, and then the commutator yx to the power k plus k prime and plus n times m prime. And if you look at the multiplication law for such matrices, you will see that it is the same. So for A and B, if you have another such matrix, 1, 1, 1, A prime, B prime, C prime, and you multiply them, you will see that A and A prime are added, B and B prime are added, and then C and C prime are added, but also we add to them something like A times B prime, or maybe B times A prime. So it's the same group. Okay. Well. Yeah. Okay. Let's leave it like this. So now we want also G to be a semi-direct product of H with Z with respect to some automorphism phi. So what is this automorphism phi of this free-nilpotent group? Well, I suggest to use the following automorphism. Phi of x equals y inverse, and phi of y equals yx. To see that it is an automorphism, we can just write its inverse. So phi minus 1 of x, phi inverse of x, is xy, and phi inverse of y is x inverse. You can check directly that these are mutually inverse to each other.
Почему без физ аж ваш штрих?
Wait, sorry.
Еще там наверху, ниже в левом верхнем углу.
Ah. Okay, yes, this is H. Yes, thank you. So, well, we have phi bar from the abelianization of H to itself, and is given by the matrix zero, 1, minus 1, 1. And if you subtract phi bar minus the identity, so 0, 1, minus 1, 1, minus 1, 1, 0, 0, you get minus 1, 1, minus 1, 0, which is non-singular. Its determinant equals 1. So it is surjective.
А есть какой-то умный способ придумать автоморфизм так, чтобы он какое-то соотношение сохранял? В смысле, он придуман просто потому, что он очень простой или как-то по-особому?
Well, to tell the truth, it comes from geometry, and you will see how. But if you want to construct such automorphisms algebraically, probably there is some approach to that, but I don't know about it. So now to finish this example, I want to construct two elements in G which map to the same element of the abelianization but are not conjugate. So I take Q to be, yes, I think we didn't quite finish. So we had every element of H has this form, and we have the multiplication law for H, for elements of H. But we also want multiplication law for elements of G, and we also want some standard form for elements of G. Well, there is, so G has the following presentation. It is, well, the presentation of H that we had before, and we add to it one new generator T, which corresponds to this generator of the mapping torus geometrically, and we add relations of the following type. So well, it's enough to do it for X and Y because they are the generators here. So X conjugated by T is phi of X, and Y conjugated by T is phi of Y. And as you probably remember from some previous proof, these relations do hold in G. And the question why they are enough, why there are no other relations, well, I think we in some way we already discussed this because we considered some map from this semi-direct product to the fundamental group of the mapping torus. And if we believe that that map is an isomorphism, then I think it should follow that there are no other relations. But also this is a standard fact from the theory of H-N extensions. So again, you can look at any book about H-N extensions, and it's written there. So now I claim that we can write every element of G. So for any G in G now, this was G in H indeed, and now we have G in G, so G can be written in the following form. So I want first to go first t to the power k and then h for some h in h.
А разве вот это вот, вы сейчас говорили посмотреть в книжке, почему g равно вот тому, что написано, да? А разве это не определение просто полупрямого произведения? То есть...
Okay, it is close to the definition of semi-direct product, but usually the semi-direct product is defined by multiplication table, for example. Or well, it depends on how you define the semi-direct product. So anyhow, so why any element has this form? Because certainly it has the form t to some power k1, h to some power l1, and then t to some power k2, h to some power l2. But then you can move all t's to the left by using the following relation. So t, well, so from these two relations we actually have that h to the power t equals 5h for any h in h. And this is the same as, well, okay, t inverse ht equals 5h, but I can rewrite it as ht equals t times 5h. And in this way I can move all instances of t to the left, and what remains is an element, so this will be an element of h. So any element has this form, and if I want to multiply to such elements, t to the power kh times t to the power k prime h prime. I'm just using this identity, and I'm getting t to the power k plus k prime times 5 to the k prime of h times h prime. So here I apply this automorphism phi k prime times. So now we have a standard form and multiplication law for all elements of G, and we can simply verify this statement for specific elements. So I want Q to be just T, and Q prime will be T times xy. So when we send this to the abelianization, so what is the abelianization? The abelianization is a quotient by this h, as we proved before. So when we do the abelianization, then this guy goes to t to the power k. So both of these guys will go to t. Okay, so this is multiplicative, or if you prefer, this is the same as k in z. This is multiplicative and this is additive. So it remains just to do some computation showing that this guy is not conjugate to this guy. So is it okay if I just do the computation? Any questions? It's not very long, so maybe I can just do it and then there are no questions left. So suppose that q to the power g equals q prime for some element g in g. So that g is of the following form: t to the power k, x to the power l, y to the power m, and the commutator yx to the power n. For some k, l, m, n, and z. And we can simply compute. So q to the power j is the following thing: t to the power k, x to the power l, y to the power m, and the commutator yx to the power n, inverse, then t, which is our q, and then t to the k, x to the l, y to the m, and the commutator yx to the n. So next, I want to bring t to the left, and I can do that by using this identity, and I get the following: t times phi of x minus l, y minus m, commutator yx to minus n plus lm, and then yes, so this t to the k inverse and this t to the k, they cancel, so I don't have any t. Well, when I take the inverse, this already becomes yx to the minus n, y to the minus m, x to minus 7, t to minus k. So here we have t to minus k, t and t to the k. So these two cancel out, and we have only t remaining. And then yes, so I bring x to the front here, and this is why I have this ln, because I'm commuting x with y, and I'm using these powers. So this is, and then I apply phi because I bring t to the left, and I'm using this identity. And then times x L y m and yx to n. So this is just the same as we had. So let me continue here. So this equals T. So now I'm computing phi of this stuff. Well, maybe I should do it separately. So if I have phi of x to the a, y to the b, and yx to c, then what is it going to be? Well, first let us, okay, so there was the formula for phi. So phi of x is y inverse, so this will be y to the power minus a. Phi of y is yx. So then I'm writing yx to the power b. And then I can write phi of yx to the power c. Now what is phi of yx? And what is this? So well, maybe this we don't need anymore actually. Well, let's see. So phi of yx equals the commutator of phi of y and phi of x, which is, I think, yx comma x in y inverse. And this is the same as the commutator of x and y inverse. You can check this using the commutator identities, and this is the same as the commutator of yx to the power of y inverse. And again you can check this. Well, let us check this. So y inverse, I'm conjugating by y inverse, so y, and then y inverse x inverse yx, and then y inverse. This is this. Now this cancels and we get this, which is precisely that. And now this is the same as yx, because in our group all commutators commute with everything else. We have, our group is nilpotent of class 2. Okay, so we found phi of the commutator, and we also need to find this yx to the power b. So this is yx b times, and we want to bring all x's to the left. So when we bring the first x to the left, we have to permute it with one y. The next x has to be permuted with two y's, and so on. So this will be x to the power b, y to the power b, and yx to the power 1 plus 2 plus so on. And the last one will be permuted with b of y's. So plus b. And this sum is b times b plus 1 over 2. So this thing equals y to minus a, okay, x to the power b, y to the power b, yx to the power b, yes, to the power b times b plus 1 over 2. This was this term. And then we need find the commutator, which we found here, which is just the commutator, right? Yes. So here I'm just writing the same commutator yx, so I can add it here, plus c.
Возможно, тот факт, что φ сохраняет коммутаторы, можно было короче. Множество коммутаторов — это в точности множество элементов, для которых коммутатор x — это множество элементов, которые совсем коммутируют. Оно ведь автоморфизм должен его сохранять.
No, this implies that phi sends every commutator to some commutator, actually to some product commutator, but we want the exact commutator where it goes. So I think it has to be computed. It will be different for different phi's. It depends on. We are lucky that we got the same commutator. For different automorphism phi, we could get something else. So here we still have to move x here, which gives us x to the b, y to the b minus a, and then this commutator yx to the power minus ab, it says minus ab, and plus this stuff, b times b plus 1 over 2 and plus c. Yes. So this is the formula for phi of an element of H, and we can now apply it here.
Простите, а откуда плюс ЛМ? Вот справа. Нет, совсем. Вот плюс ЛМ.
This one we got, so this was inverse. So when we write it out, we had this, and we want to bring x to the left. And this is still before we apply phi. Of course, we can do it after we apply phi, but anyhow, we have to do it. Okay, so this becomes x2 minus m, y2 minus m plus l. Commutator yx2 minus m plus lm minus L times minus M plus minus M times minus M plus 1 over 2, and still we have x to the L, y to the M, and yx to the L. So yeah, I checked this formula actually only for positive b, but I'm going to apply it for negative b. But maybe you can believe me that for negative b it works the same. Well, actually I don't know. I don't know if it is positive or negative because I don't know if this KLM and are positive or negative.
А можно как-то вот
You
сразу понять, что если это положительное, то для всех, в принципе, такое соотношение, ну, любое, если верно.
Maybe you can certainly check it for negative. You can.
Но вы знаете, что не проверяя. То есть не может же быть такое, что для всех положительных верно, для какого-то отрицательного неверно. В принципе, для любой такой формулы.
Maybe there is a way of doing that, probably, but I cannot tell now.
Вот в теории этой группы, видимо, должны быть неопределимы отрицательные целые числа, вот, потому что нельзя единицу от минус единицы отличить.
Could be.
Вот это формула выводит.
Could be. Okay, so we have just one more. Well, and no, so we have this minus m from this minus m, this minus m. Where do we get it? X to the. So here we have x to the power b. Yes. So we actually get it also from this. Well, so you can check that. I'm just applying that formula and I'm getting this. And now the last step is just to bring this to the front, and so I have essentially I just want to move x beyond this y, and this will so I have to multiply L by this. Okay, so this is t times x to the power L minus m. So I think this is, how do we get L minus m? This L, so we have minus m plus minus m plus L times L. So and this, Что?
Это для Y,
No. Sorry. This is for the commutators. To find the power of x, we just add this L and this minus m. Oh, sorry. This L minus m is just this L plus this minus m. And then y, we're just adding this m and this minus m plus L, so we are getting y to the L. And then we have the commutator yx. So now we have this L times L minus m, which comes from bringing this x to the left, beyond this y. And then everything else. But if you look at this everything else, It looks like I have something missing here. Okay, so this is Lm. So these two actually cancel out. Okay, so this is m times m minus 1 over 2. So we certainly have m times m minus 1 over 2. But I think we also have this minus n. And I don't have it. For some reason, I forgot it. No. Here we have n, and here we have minus n. And they also cancel out. So we don't have it. So this is what we get. And this is, so this was q to the power g. And this is supposed to be equal to q prime. And q prime is t x y. Okay, so if these are equal, then we have L minus M equals 1. This one equals this one. And this L equals 1. So this implies that M equals 0. So then this stuff equals 1 times 1 plus 0, this is m is 0, so this is 1. But here we don't have the commutator. So this commutator yx has 0 power here, so this one must equal 0, and this is a contradiction.
А можно вот общий вопрос насчет построения такой группы. Вот если взять какую-нибудь просто вообще любую группу, у которой абилизация это z, ну там вот группу дополнения к узлу какому-нибудь, и вот ее профакторизовать по вот ее степени 2,5, то тоже получится вот такая группа. Вот если так сделать, там не удается просто найти.
Yes, but you need some explicit group, and so I just took some explicit group. This is a very simple group. So you see, I started by, so this is what I want. I started by analyzing what I want, and I obtained that we need our G to be of this form. Yes, and H, so the semi-direct product of H and Z, where H is nilpotent of class 2. So if you take H to be nilpotent of class 1, it means that it is abelian, and this will not work, because it will be, we had this lemma here for where we had 2 instead of 2.1, and there is no such example if you replace 2.1 by 2. So definitely H must be not nilpotent. And this is the simplest group, this free nilpotent group of class 2, well, it is one of the simplest groups which is not abelian but nilpotent.
Являются ли группы гладких узлов метабелевыми?
No, but we can take their quotient by the second commutator subgroup, and then we obtain metabelian group.
Все-таки, простите, вот это я не понимаю, почему нельзя взять группу вот такого узла, профакторизовать ее по 2,5 степени, и вот поискать там такие куштрихи.
This is actually what we are going to do next.
А зачем, если мы уже такую же нашли? Нет, я имею в виду, если мы хотим, то есть не можем ли мы это сделать, чтобы построить такую же? Мы сейчас вот строили такую же.
Yes, but this construction is as simple as you can do. From the algebraic viewpoint, it is not possible to do anything simpler, because it has to be of this form, where H is not abelian. And I took H to be the simplest non-abelian group which exists, in some sense. So I'm doing.
В смысле, из этой же будет простейшая конструкция вытекать?
Yes, so I think this is the simplest possible construction from the algebraic viewpoint. If you want to start from topology, you can do it, and you can start from topology, but I think you cannot avoid these computations anyway.
Вот с алгебраической точки зрения вот такая же сложна в том смысле, что вот когда мы ее через образующие соотношения записывали, там все-таки вот куча их, там в H, вот то, что коммутатор с M коммутирует, потом то, что это было прямое произведение, а если взять какую-нибудь группу триглистника, то там, ну, очень просто.
This is exactly what I'm going to do next. Take the trefoil knot and see that we have this example inside the trefoil knot. Okay? So maybe. So do people want to have a break now, or we first bring this algebra into some geometry, which I hope will be quick enough. Any?
Well, I think you talked now for 2 hours already.
So you want a break, yes? Okay.
I think you should have.
Okay. Let's make a break now. So after the break, then I will do geometric constructions which depend on this algebraic construction. Okay. So a break for approximately 20 minutes. So now I'm going to do another example. Example 2. So now we look at the trefoil knot. So Q will be the trefoil knot. And the claim is that the fundamental group contains elements AB which map to the same generator with some alpha in H1 of the complement, but their images, let me call this group pi. So their images in pi modulo pi 2.5 are not conjugate. So eventually we want to construct a wild knot and 2 meridians with the same property in the complement to this wild knot. And this is because we want to use the construction of Andreas, which for each meridian gives us an isotopy to the trivial knot. So we want meridians of a wild knot, but so far let us construct some elements, not necessarily meridians, for a tail knot, for a trefoil. So the secret is very simple. the trefoil knot is fibered. So there is a fibration S3 minus Q fibers over a circle. It's a fiber bundle actually, and the fiber is let me call it F. Yes, F is a good notation for the fiber, but also F is a Seifert surface. For the trefoil of minimal genus, which in this case equals 2. So in fact, I think there is a theorem that the Seifert surface of minimal genus is unique for every knot, and if this knot is fibered, then this Seifert surface of minimal genus is the fiber. Well, okay. Uniqueness, I don't know about uniqueness, but every Seifert surface of minimal genus is the fiber of some fibration. This is so not true. Good question. I think it is unique in some sense, but I think we don't need it. So in our case, yeah, the fiber is punctured torus. Which is a Seifert surface for the trefoil, and then we come essentially to the previous situation. So the fundamental group so this was the pi, the fundamental group of the complement. It is isomorphic to pi prime semi-direct product with z. So pi prime is on the one hand it is the commutator subgroup of pi, but on the other hand it is the fundamental group of the fiber. And z is essentially the generator of the fundamental group of S1, which is the base of the fibration. So there is a theorem in knot theory that you for every fibered knot, so not every knot is fibered. There exist knots which do not admit such fibrations, and those knots which do admit such a fibration, such a fiber bundle, are called fiber knots. But the theorem says that for every fibered knot, we have the following isomorphism. Its fundamental group is isomorphic to the semi-direct product of its commutator with Z, and moreover its commutator is the fundamental group of the fiber. And you can find this theorem, for example, in the Burde and Tishank textbook.
А полупрямое произведение разве не всегда будет?
You mean this isomorphism always holds?
Там же достаточно расщепления. Yes, okay, this isomorphism always holds. Yes. But this isomorphism, this is not always true. So if the knot is not, another theorem says that if your knot is not fibered, then this commutator subgroup is infinitely generated. And in this case it is of course finitely generated because it is the fundamental group of a surface. So you can find this theorem in the textbook called Burde and Tishank.
Okay, so in our case, this fundamental group of the fiber is the free group on two generators, so x, y, and no relations. And now if we take the quotient by pi to 2.5, then by previous arguments, so there is this automorphism phi, and there is a question: is it true that phi bar minus the identity is surjective? So if this is true, then we get simply that this quotient is isomorphic to pi prime modulo. Okay, let me be. It is true, but we actually don't need it, and what we need is that this homomorphism from pi to pi modulo 2.5 factors through the group of the previous example, actually. And the group of the previous example is our H semi-direct product with Z. So H is the Heisenberg group. The discrete Heisenberg group, which we free nilpotent group of class 2. So actually I claim that we just have this. In fact this is going to be isomorphic, but we don't need it. And yes, so phi bar is going to be precisely our phi, but so let's compute it. Maybe I can make some more general statement here that if this thing is surjective, then we already get something good. But indeed, what we actually need is to relate this to the previous example. So let's just do that. And for this, we need to do some computations in the fundamental group. So let me draw the trefoil. Not very beautiful.
Кажется, одно пересечение между нами.
Да. Спасибо. So let me first write a presentation of its fundamental group. So I want to use the following generators: P, Q, and R. And then we'll have the presentation P, Q, R. So this is a working representation actually. If you look at this, every arc every arc of this plane diagram, there are just three arcs. So the relations are as follows. PQ inverse equals R inverse P. Q R inverse equals P inverse Q, and R P inverse equals Q inverse R. And actually any one of them is redundant. Any two implies a third one. So these relations correspond to the three crossings. So for example, let's look at the first relation. The first relation corresponds to this crossing. So we have P Q inverse equals R inverse and then P. And similarly for the other two, you can check that they come from, the second one comes from this crossing Q R inverse Q R inverse equals P inverse Q. Yes. Okay. Now I want to compute them on algebra. I want to compute phi. Because I want to relate it to the previous example. So let me draw some Seifert surface to start with. Well, so this is an orientable surface because you have three twists here, but as you can see, whenever you go by any two twists, the orientation is preserved. So now I want, and maybe you can see that this surface is a punctured torus. So I want also some generators of the fundamental group of this surface. And I will use the following generators. So this will be the base point, and then this will be X, and this will be Y. so you can see that we can express x and y in terms of the generators. But yes, maybe I should. So this is the fundamental group of S3 minus Q. And we also have the fundamental group of the surface. So this is the surface. And it is generated by x and y, and there are no relations. But also there is, well, at least this map actually it's injective. So I can write x and y in terms of p and q, and namely this will be x and this will be y. So you can see x is first we go R inverse, there is R, and then we go P. R inverse P. And similarly y, first we go Q inverse and then we go P. Oh. Y, Q inverse and then P. And then yes, P. Right. Oh yes, I have wrong orientation for y. Why use this? Then indeed it is P inverse Q. Okay. So now we can find the monodromy map phi. So to compute this monodromy map, yes, so we have the short exact sequence. This group by one of F goes to by one of S3 minus Q goes to Z. So to determine phi, we need to choose some splitting F. And I suggest to use the following splitting. F of the generator, or F of 1, equals P. So then phi of G will be G conjugated by P for G in this group. So let's compute it on generators. Phi of x, x is x to the P, and x is this, but let us use this relation. So I can write x as PQ inverse, and then I have P inverse, PQ inverse P. This is Q inverse P. Q inverse P. And this is Y inverse. And now phi of Y is Y conjugated by P. Now for Y, I suggest to take also this QR inverse. So it's P inverse QR inverse P. And this is simply P inverse Q R inverse P, which is Yx. And so we get the same homomorphism as we had before. X goes to Y inverse and Y goes to Yx. Of course, here it is an automorphism of the free group, but when we take the quotient by this pi to the 2.5, anyhow we can take the quotient of this free group by its gamma 3, and then we get just this Heisenberg group, and we get the same automorphism here. So this homomorphism is constructed, and this map should factor from this through this homomorphism, because this group is 2.5 solvable. So, and this can be proved in the same way as we argued before the break. So we know that H is nilpotent of class 2, and we know, and also we know that phi bar minus the identity is surjective. Because we checked it for the same phi. And then this means that H, so if this is called G, then H equals G prime, and then since H is nilpotent of class 2, we get that G is 2.5 solvable. And then this factors through this one. And so in the previous example, we have shown that there exist two elements of this group G which are not conjugate. And now we want to get, so we can take their primitives in pi, and of course they will be not conjugate here because they are already not conjugate here. No.
Кажется, стрелка должна быть.
You're right. Yes. Yes. This arrow should go here. So the claim is that this. So we have this arrow definitely, and the claim is that it must factor through this. Yes. And this is true since this group is 2.5 solvable. Yes? So all the relations which are obtained by taking this quotient already hold in this group, so we can add them first and then add whatever else is in there. Actually it is an isomorphism, but we don't need this. Yes, so if I take the, so we had these elements Q and Q prime here. If we take their primitives in pi, then their images here will be not conjugate because they are not conjugate already in this group. Okay. Okay. So I think example 2 is done. Any questions?
Я упустил Существует ли способ проверить 2,5 разрешимость вот группы справа быстрее, чем через вот абсолютно явное выписывание элементов в общем виде?
I think maybe there exists some other way, but the way which I know is using this property that phi bar minus identity is surjective. And then we need at least to determine phi. So I'm not sure if it can be simplified, maybe.
Понял.
Okay, so I think now we are ready to prove proposition 2. So I want to construct a wild knot and its two meridians which are not conjugate even modulo this 2.5 derived term. So first of all I need a picture of a wild knot. And it will be this alternating one. No. I think I confused something again. Okay.
Здесь имеется в виду, что если вот так на него посмотреть, то будет Т-листник.
Yes, absolutely. So this is the wild knot, and this will be the two meridians. So I want one meridian here and another meridian here. No, this is also not right. Okay, so it consists of two tame arcs. Let me call them A and B. So S3 minus A is homomorphic to S3 minus a point, which is homomorphic to R3. And R3 is homomorphic to the infinite cyclic cover of the complement of the trefoil knot. No, the complement of the trivial knot. Let me call it U. U is a knot. So its complement is homomorphic to the open solid torus. S3 minus U is homomorphic to S1 cross R2. And when you take the infinite cyclic cover, you will get just R3. And inside of this S3 minus U, I suggest to take a certain knot. Now I think I need to draw a picture.
Другое пока никак не задействовано.
Yes, I want to use dark B. So now I need the following picture. Now let me draw this in pink color. I'll draw something here in pink color. And and this is U, which is our unknown. Now this is Q. So we have a two-component link. But as you can see, this tame node Q reminds a little bit this picture. So if you look at this fragment here, it is the same as for example, this. How about this? Actually, when you take this Q in the complement of the unknown, then we have this infinite cyclic cover, and we can take the preimage of Q in this infinite cyclic cover. And the claim is that this will be precisely our second tame arc B. I mean, you can find such homeomorphisms which will identify it with B. So this Q sits in the solid torus essentially, this solid torus S1 cross R2. And when you unwind this solid torus, you will get precisely infinitely many fragments like this. Is everybody okay with this? No? Andreas, any questions? Andreas, are you okay?
Sorry, I was muted. So I was lost. I was trying to follow the construction, but
Okay. So let me start from the beginning. I'm constructing a certain wild node. I just constructed by showing a picture.
okay.
Now I claim that so it consists of two tame arcs. As you can see, it has two wild points, which divide it into two tame arcs.
Okay, now the question is, do the endpoints belong also to B or not?
No, they do not belong either to A or B. They are separate. A and B. Okay, they belong to A. Yes, this is a good question. P and Q, let's put them into A. Yes.
They belong only to A
And not to B.
and not to B.
So then, if I subtract A from S3, it's the same as if I subtract a point from S3. And this is R3. And I can also understand R3 as the infinite cyclic cover of this solid torus S1 cross R2. But now this S1 cross R2 can be understood as a complement to the trivial knot, to the unknot U. And so we are taking the infinite cyclic cover of the complement to the unknot. On the other hand, in this complement to the unknot, I will find a certain knot Q, certain tame knot. Here I show this knot. And if I take the preimage of this tame knot Q under this infinite cyclic cover, I will get simply infinitely many copies of this picture in this space, which is R3. And here is exactly how it looks like. So the claim is that this preimage of Q can be identified with B, with this tame arc B, if we choose this homeomorphisms appropriately.
I'm now with you.
All right. Now we can also see where these two meridians go under this projection from the cover. So,
Простите.
ага.
Здесь важно, что r в кубе, которая получается из сферы без А и сферы без и как циклическое накрытие сферы без У это одно и то же пространство. Это важно, что вот оно там одно.
Важно. We need to ensure this homomorphism. Yes, because we want to identify the preimage of Q which lives in this space, with B which lives in this space.
Странно, учитывая, что вот так изоморфизм, вот так композиция и накрытие еще вложение.
So we can start from this picture at the bottom. If we take the infinite cyclic cover of the complement to the unknot, so the complement to the unknot is this solid torus. When we take its infinite cyclic cover of this solid torus, we just get infinitely long sausage which contains infinitely many copies of this picture. So this picture just repeats infinitely many times, and this is precisely what we have here. Except that I should really, instead of P and Q and this arc A, I should really draw just one point, maybe a point at infinity. Yes, so if I identify this with R3, this infinitely long sausage, if I identify this with R3, then instead of P, Q and this whole arc A, I will have just one point at infinity. But it doesn't change anything if I enlarge this point to an arc. Okay? Is it better now? So let's look at the images of these meridians. So I think I call this J1. No, this is J2. And this pink one is J1. So this one will go here, and this one will go where? Here. Yes. So, in order to show that J1 and J2, so claim the classes of J1 and J2 are not equal in pi 1 of S3 minus this wild knot, it's called A union B, and modulo, let me just write 2.5 here, which means the subgroup, the derived subgroup of this of length 2.5. So in order to prove this, it is enough to prove that this J1 prime and this J2 prime, which is the image of J2, J1 prime, no, not conjugate, to this one. So this one not conjugate to J2 prime in the fundamental group of the complement to this link. Yes, 3 minus, okay, pi 1 of S 3 minus U union Q. Because the complement to this wild knot goes to the complement to this link under this map. We actually have a map from this complement to this complement, which is this infinite cyclic cover restricted to this to the complement of this preimage. So if this were conjugate here, then of course their images would be conjugate. And in order to prove this, it is enough to prove that they are not conjugate to J2 prime in the fundamental group of the complement to just Q. So it would be enough to show that they are not conjugate in the fundamental group of the complement to this two-component link consisting of Q and U. But I will throw this unknown away, I will forget about it. I will show that even in the complement to this Q they are not conjugate. And actually, you have already probably guessed why they are not conjugate, because Q is a trefoil. It is the same knot as this one. Why? Why is it the same knot? So I need to draw some new picture.
4 пересечения, от одного можно избавиться от самого верхнего, если внешнюю дугу просто наверх перебросить.
Yes. So first of all, we need to. I'm erasing this unknown because we don't need it anymore. So we just have this knot. So first of all, we take this arc on the bottom and move it to the top. Maybe I can just erase it here and redraw it. Okay, so this is the same as before. I just moved the arc from the bottom to the top. I can simplify it a little bit. And also here, but then I have to move this meridian. Okay, I think I need to draw a new picture. Yes. I want to turn this this loop. I want to rotate it like this, but I think I should draw it. Okay, maybe. Okay, so after you flip this loop, you will get this picture, and you can see that this pink loop will look like this. If you just bring it here and follow the flipping. So this is still J2 prime. No, J1 prime. This is J2 prime. And now, to get from this picture into this picture is just a matter of changing the geometry. The topology is the same. So so here you have 1, 2, 3 crossings, and here you have 3 crossings. And I claim that these are the same crossings. And one way to see this is to identify this arc. I suggest to identify this arc, or maybe this pair with this pair. Yes, I think that's correct.
Там двуугольники тоже цепочкой идут. Вот маленький и потом вот этот вот большой.
So more precisely, this one is this one, and the other one is this one. And then when you move here, for example, you get to another crossing, and this corresponds to moving along this arc and getting to this crossing. You can also get from it to there, which corresponds to this arc. And it's basically all. And then the question is where these 2 meridians go in this picture. And here's where they go. So J2 will be just here. And J1 will look like this. This is J1 or J1 prime. That was J2 prime. Okay. So in terms of this, well, it's quite clear that J2 prime goes here, and for J1 prime, well, you can kind of see again, there is no topology is not changed, only the geometry is distorted. So it crosses this arc once and this arc two times. It winds 2 times around this arc, which corresponds to this double winding. So you can kind of see. So now what is what are these elements in the fundamental group or conjugacy classes? Well, J2 is, I think, just P, So the class of J2 prime is P, as you can see. And the class of J1 prime, well, let's see. It's if we start here, for example, then it's again P, then P, so P squared, and then here is R. So it's P squared R. No, it should be P squared R inverse. Yes. So R goes here, and this J1 prime goes in the opposite direction. P squared R inverse. And this is the same as Pxy. So let's see. This is the same as P times PR inverse, and if I write X, so I can write it like P times PQ inverse times QR inverse, and this is Pxy. Using again these two forms of X and Y. And so as you remember, we decided that we choose a splitting which sends the generator of Z into this P. So we have conjugation by P. So in terms of our first example, the algebraic example, this P should be written as T, because it was a generator of Z which acted on the discrete Heisenberg group. So you can call it Txy, and this can be called T. And as you remember, we have proved that precisely T and Txy are not conjugate modulo the derived term of 2.5 term of the derived series precisely for this trefoil group. So I think we have proved proposition 2. Questions? Uh-huh.
Does it matter if you choose a different meridian of the knot? Of the little,
Do you mean this while not?
No, the knot down below. The
This.
lower knot. If you, it looks like green or blue.
Yeah. Well, this is a meridian, and all meridians of trefoil or of any tame knot are the same. You can move them around. This is not a meridian here, but it comes from this meridian. Actually, I didn't say this. So you can move this meridian through this wild point, and then it becomes a curve like this. And this is how you get this J1 prime. Yeah, so it was a meridian here, but this is no longer a meridian. And
I just observed. I just was. I'm looking at the picture. I can see that if you were to move slide that meridian around, it would be clear that loop, the bigger loop, is let's see. It times the inverse of the meridian is a commutator, just because they bound the surface.
Yes.
I don't know if that
Yes.
play a role in your computation.
Certainly they bound a commutator because they have linking number 1 with with this trefoil.
Oh, okay, yeah.
So here in the top picture, I think there are just two meridians, because this stem arc A has basically one meridian and this stem arc B has one meridian, because no matter where you put it here, it's the same meridian. So for this picture, there are, I think, no other choices of meridians, but of course if you have some more complicated wild knot, it can have many different meridians, depending on how many wild points it have. And of course, if you start from the being sling doesn't have any meridians. Okay.
Что вы называете меридианом?
So I call by meridian a loop in the complement to a knot, possibly wild, which bounds a disk, such that this disk intersects a knot in a single point, and also the disk locally separates a knot at this point.
Правда ли, что у любого дикого узла с одной дикой точкой есть вот два различных?
Well, I think if we have just one wild point, then all meridians will be the same. But if we have two,
здесь то есть одна, ну вот такие две, это одна на самом деле.
Okay, yes, yes. Actually, you can really squeeze this arc into a point, and you will still have a meridian passing through this wild point. Yes, it's true. Yes. Well, it depends, because if you have the wilder arc, and close it up like this, then this for this knot all meridians are the same. I think the matter is that here it sort of approaches this wild point in a wild way from one direction, and here it approaches it in a wild way from both directions.
Там, если в другую сторону продолжить, все равно один меридиан будет. Вот если нижний пример, в другую сторону тоже.
So if you start with this meridian, then you can move it here. Yes. Is this what you mean?
Не важно, но вопрос тогда, вот если нету, ну вот можно, вот у других, с всего одной дикой точки можно нарисовать диаграмму. Вот если у нее нет, просто вопрос вот в чем, вот здесь очень удачная конструкция, в которой получилось доказать, что меридианы сопряжены вот в этом ноде. А известно что-нибудь про вот общий случай. Ну, вот, допустим, узел такой, что нельзя нарисовать диаграмму, значит, одна дикая точка, нельзя нарисовать диаграмму такую, что будет мост.
Что значит мост?
Ну, это вот когда вот есть дикая точка, есть вот этот мост, и вот на такой прямой больше ничего нет, вот просто справа что-то, слева что-то. Ну, если мост есть, то ясно, что можно с дикой точки перекинуть вот, через бесконечность окружность на дугу.
Well, anyhow, I just have this example, and I don't have any general results about arbitrary wild knots. Well, maybe you can prove it, but another question is why one would be interested in them. But there is actually one more thing to tell. So, if any questions to this, or I can continue. No. So there were two versions of proposition 2. So in one version of proposition 2 there was 2.5, and there was another version actually from last time which had 2.4 or 2 plus, you can call it. So it's a stronger version. Let me recall what it means. So G 2.5 is the commutator subgroup of G prime and G, no, let me write it like this, G, yes, G prime and G prime prime. And G 2 plus is the commutator subgroup of G prime and T hat, where so we have the module, this G prime over G prime prime is the module over the Laurent polynomials set of T plus minus 1. Because this is a homology of the infinite cyclic covering, for example, or because T acts on, because again we have this short exact sequence, and if you choose a splitting, then again the generator T acts on this G prime prime. So this is a module, and we can choose, we can fix it torsion submodule. So what is the torsion submodule? It consists of all elements which can be annihilated by multiplying by some Laurent polynomial. So T is the set of all M, such that there exists a P, a Laurent polynomial P, such that P dot M equals 0. And then there is the map from G prime here, and then T prime, T hat. Yeah, let's call it P, for example, and then this will be the preimage of T. So this is something which lies between G prime and G prime prime. And G2 plus is this commutator subgroup. And proposition 2, another version of proposition 2, says that even modulo G2 plus, these two meridians are not J1 and J2, they are not conjugate even modulo G2 plus. So the same example. And the reason why this happens is very simple. Is that because in this case T is 0. So this module is torsion free in this particular example. So lemma that G prime modulo G prime prime is torsion free over Laurent polynomials.
Утверждение в том, что эти элементы сопряжены.
Well, if we prove this lemma, then we actually get that in this particular example, this T hat equals G prime prime, because T is 0 here, and so this preimage is G prime prime. And then yes, they are not conjugate because they were not conjugate modulo this. So I don't know if you want me to prove this lemma, or maybe it's too much for today. The proof of this lemma is algebraic. So actually I just construct a presentation for this module, and then so maybe if I skip the step of constructing the presentation, then this proof is very simple. So maybe I can tell you that. Is that okay? So I think I can erase all of this now. Okay. So claim which I will not prove, but it's a computation. So is that this a presentation of this module is as follows. So we have generators xi indexed by all integers, positive and negative. And then for each I we have one relation. No, I think there is not enough room. Okay, let me write Ri, I in Z. Ri is Ri equals 1. Ri equals 0. So Ri is the following thing. 1 minus t inverse xi plus 1 plus 1 minus t xi minus 1 plus 2t plus 2t inverse minus 3 times x. So this equals 0. So somehow by a miracle we have this, a miracle happens and then we have this presentation. Случилось чудо, и у нас появилось это представление. So now I claim that this module is torsion free, and to prove this, I need a lemma. So we have here, so maybe I should write that this is isomorphic to H1 of the complement to our. Well, so here we really have this B. So I can write R3 minus B, or I can write an infinite cyclic cover of that, or I can write S3 minus A union B, and the infinite cyclic cover of that. So A union B is our wild knot, and this is just its infinite cyclic cover. So this is the same as this quotient, and so we had the lemma in the first seminar that if we consider the multiplication by 1 minus t over on the first homology of infinite cyclic cover of any wild knot or tame knot, then this is an isomorphism. So in this module, every element is divisible by 1 minus t. So Andreas wrote me in email that he cannot see it geometrically. Well, I agree that this is not obvious. This is not obvious. Maybe it's possible to see it geometrically, but I have to. It should be possible, but I have to think about it. So, anyhow, we proved this. I think it was an honest proof, and I'm going to use it. So, because every element is divisible by 1 minus t, I can also consider this this abelian group as a module over a different ring. So let me introduce this ring. So I take the ring of Laurent polynomials and then I localize it by allowing to divide by 1 minus t. So it can be written like a ring extension when I just add this element to this ring, to the ring of Laurent polynomials. That's a localization. It's a usual localization. So it's how can you say otherwise? So yeah. So there is the multiplicatively closed set consisting of the powers of 1 minus t. Now I equals 1, 2, and so on. And we can consider the localization of Laurent polynomials with respect to this multiplicatively closed set. It's the same as this extension. So we can consider our abelian group G prime modulo G prime prime or this homology also as a module over this ring R. And if we do this, then we are allowed to divide by 1 minus t. And then this relation will be simplified. So as well, first I must say that if we consider it as an R module, then the same presentation as we had, it still works. Because, well, we just took a localization and the original relation still works. But as an R module, it can be simplified. As an R module, G prime over G prime prime also has the simplified presentation. So what is a simplified presentation? Well, I can divide by 1 minus t, for example, and then I can express xi minus 1 in terms of the other generators here. So xi minus 1 equals 1 minus t inverse. Maybe I can put a minus here, and then everything else, 1 minus t inverse xi plus 1 plus 2t plus 2t inverse minus 3 xi. Okay, so it has a simplified presentation with these relations. Or I can simplify them in a different way. I can divide by 1 minus t inverse, because 1 minus t inverse, if we multiply it by t, then we get t minus 1. So I can write 1 minus t inverse equals minus 1 minus t inverse 1 minus t. Yes? Yes. So t inverse we have in Laurent polynomials, and we can divide by 1 minus t. So we can also divide by 1 minus t inverse. And then I can write xi plus 1 equals 1 minus t inverse minus. And okay, let me not write the bracket, it's something else. But in this way, I can also express xi plus 1 in terms of xi and xi minus 1. And then I can actually start with just two generators, for example x0 and x1, and I can express x2 in terms of these two by using this relation in the bottom, and then I can express x3 in terms of x1 and x2 by using this relation in the bottom, and so on. So I can add x4 and x5 and so on. Also I can add x minus 1 by expressing it in terms of x0 and x1 by using this previous relation. And then I can similarly add x minus 2 by expressing it in terms of these two, and so on. So all generators are expressed in terms of x0 and x1, and we don't have any relations on x0 and x1. So it's because we have used up all our relations when expressing other generators. So this is a free module on two generators. So as an R module, it is a free module on two generators. But in particular, this means that it has no torsion over R. But then it has no torsion over Laurent polynomials. Okay, so it's 9 o'clock now. Yes, any questions? So I was planning next to tell some motivation of the definition of n-bordism and also advertise the isotopic realization problem. So I don't know if you want me to do this or it's better to stop now.
Better to stop now.
Okay. Okay, so, well, I'm not sure if I will continue this because I think next time Piotr Mikhailovich wants to speak, Akhmetiev. So maybe...
Я бы отошел на минуту, а потом послушал все-таки, зачем именно коммутаторы.
So maybe sometime later in the end of April I can do this maybe. We'll see. So if there are no questions, let's finish then. So thank you everyone for listening.
Есть вопрос. Вот значит, есть, вы сейчас доказываете утверждение про то, что бывают не 2,5 вариантные меридианы, а оно само было нужно для чего-то еще. Вот был один момент, когда вы говорили 4 утверждения, вот там двумя способами могла бы решиться проблема Роусена.
Okay, yes, so let me recall, yes, how this, so we have proved this proposition too, that these two meridians are not conjugate modulo this 2.5 derived term. So how do we use proposition 2? Well, we use the construction of Zastrov. Corresponding to this meridian, there is an isotopy of this while not to the unknot, which shrinks everything to one point and just leaves this disk. And corresponding to this meridian, there is another isotopy which shrinks everything outside this disk to a point. And from these two isotopies, we get a self-isotopy of the unknot. And then there was a theorem that this self-isotopy of the unknot does not extend to any 2.5 bordism. So how this is proved? Suppose that it extends to a 2.5 bordism. Then using a lemma which we proved in the first seminar, there is deformation retraction of the complement to the isotopy onto the complement of this wild knot. And then that 2.5 Bourdism, well, we can consider its image in just this one-time slice, and then it gives us an elementary 2.5 Bourdism between J1 and J2, which doesn't exist as we proved today.
Спасибо.
Okay? More questions? No? So then goodbye to everyone.